morning. We said that a detonation consists of a shock front followed by chemical reactions. In fact, what we said was you have something like a shock which causes chemical reactions to occur in the zone which is heated, and you have high pressure behind the shock, and it is these chemical reactions which maintain the strength of the shock. That means the chemical reactions are coupled to the shock. In today's class, we will try to determine the velocity with which this particular detonation wave comprising the shock and chemical reactions coupled together move, that is one velocity. We would also like to determine what is the pressure behind a detonation, what is the density behind a detonation, and also let us say the temperature behind the detonation. To be able to formulate this particular problem, we need some more thinking, because in the last class we again said that the front of a detonation is not planar surface like this, but it consists of multiple shocks. It consists of shocks, a number of them together, and not only does the front consist of multitude of shocks, but also you have transverse shocks behind, like you have shocks like this which are transversely moving, something like this over here, this over here, this over here. These shocks are moving, and the point of intersection of these three shocks here, let us say this is a Mach shock, this is an incident shock, this is the transverse shock over here, you have a transverse shock and incident shock over here. Well, the front consists of these shocks, and these shocks are also, the front shocks are also in a state of continuous decay, like for instance the triple point here O, the triple point here O traces something like a trace which is something which we saw was a characteristic cell of a detonation. In other words, when the transverse waves come and hit together, the cell gets regenerated and another cell is formed. This should have been an incident shock, this should have been a Mach shock over here. If it is an incident shock, the transverse shock should have traveled like this. When the transverse shock hit together over here, another cell is regenerated, a Mach stem shock is formed, you have a Mach shock over here. That means the front shock consists of a Mach stem shock, an incident shock, a Mach stem shock. That means it has a series of these particular shock waves, and the interaction point traverses or forms something like a cell of a detonation. And within the cell of a detonation, the shock waves are in a state of continuous decay. Therefore, it is not that the detonation wave within this cell is travelling at constant speed, but it is travelling at variable speed, always decaying. So that means it is travelling in spurts. If it is travelling in spurts, it is difficult to imagine how I can talk in terms of a single velocity for a detonation. But when the cell size is small, and also if I use the front of a detonation to be given as planar, I get velocities which are quite meaningful, which are very representative or quite accurate for the combined shock and chemical reactions for a detonation, and this is what we will do today. Having said that, let's take a look. We already saw what was the equivalent one-dimensional model, and therefore what I take a look is I come back to the slide over here. I say, well, I have a detonation here, you have a front of a detonation, I have chemical reactions occurring behind it. Well, the front travels in the unburned gas medium with a velocity v0. Therefore, in the frame of reference of the front itself, that means I sit on the wave over here, the gases approach me with a velocity v1, the gases leave me with a velocity v1, the gases approach me with a velocity v0. We wrote the energy equation, and we found this energy equation is very similar to the energy equation for a shock wave. That means a discontinuity here, except that heat is released over here, and we got the one-dimensional equation as gamma by gamma minus 1 p by rho minus p0 by rho 0 minus half of p minus p0. The pressure behind the wave or behind the detonation is p, ahead of it is p0, p minus p0 into 1 over the density ahead of it plus 1 over rho behind it is equal to the heat release. Therefore, compared to the case of a shock wave wherein we had the shock Hugoniot, when heat release is there, you get the reaction Hugoniot. And what does the reaction Hugoniot denote? It denotes the condition P and rho. That means it gives the state of P and rho behind a detonation. That means for all possible velocities with which maybe the detonation can propagate into the medium with V0. I get the reaction Hugoniot, it gives all the states P and rho behind it for any initial point which is at this point O, which is let us say P0 and rho 0. Since it is P0, since the y axis is P by P0, it is 1 over here. The x axis is rho by rho 0 is 1 point, that is the initial point is here. For this initial condition, when I have exothermicity Q, all the possible states are given by the reaction Hugoniot over here, which is the particular equation. Now in the last class we also saw that it gives all possible states, but for a given velocity, the velocity is given by the Rayleigh line, and when we talk in terms of the Rayleigh line, I could have a Rayleigh line which has this slope, a smaller velocity, or it could have a slightly higher velocity, or still a different velocity over here. And the Rayleigh line is given by rho 0 square into V 0 square is equal to P minus P0 divided by 1 minus rho 0 minus 1 over rho, which is the Rayleigh line, and this gives an indication of the velocity. And therefore, for a given velocity, if I say, well, the velocity is given by this particular slope, the slope of the line OB with respect to the axis, this is the value. For this particular velocity, well, the condition of pressure is over here, P by P0 is over here, and the density corresponds to 1 over rho, that is, this corresponds to the density, this corresponds to the pressure. Therefore, for different velocity lines, I can find out the different points. That means for a given velocity, I know what is the value of P and rho. Having said that, we also took a look at the different states which are possible. We found that when the states are above the 0 point, well, the pressure increases. When the states are below this particular point, the pressure decreases. Therefore, the compression solution should be above the point O, and that means for all these points are the compression solution. And when the pressure is lower, I said, well, the expansion solution should be here. Therefore, since we are talking of shock, we expected the solutions to be in this particular region on the reaction Hugoniot, and the expansion solution to be in the part between this and onward. Therefore, let's take a look what are the possible states behind in the reaction Hugoniot. We also found out that if I draw a vertical line from the initial condition and a horizontal line from the initial condition, the states between this and this, that is between A and B, are such that the pressure is increasing, but when I look at density, 1 over rho by rho 0, therefore the density is decreasing. Therefore, between A to B, well, the pressure increases, but the density decreases. Therefore, this is contradictory. Pressure gives a contradictory message to the density. Therefore, these states are not possible. And in fact, if I take these states here and substitute it, I get P minus P0 divided by 1 over rho 0 minus 1 over rho. This gives me a negative value of V0 square, which is just not possible. Therefore, we say states between A to B cannot exist. Therefore, only states A and above on the reactive Hugoniot line can exist, and states below, let us say B, on the reaction Hugoniot can exist. Therefore, now let us take a look at this. When I talk of a state in this particular line, A and going towards U and beyond, what is happening is the pressure keeps increasing. The density is to the left of the initial point O, therefore the density also increases. Therefore, the branch of the reaction Hugoniot from A as it extends above is the compression solution or the shock solution. Therefore, we expect the detonation to give the final solution to be over here, and we are interested in finding out the velocity of a detonation. While doing this, let us also take a look at the expansion effects over here. We find, well, between B, L and beyond, the curve is over here. You find that the pressure decreases. Well, the density is also decreased over here, and therefore, since the pressure is lower and the density is lower, it corresponds to the expansion solution, and therefore the region between this and this should correspond to a flame or a deflagration. Now, we want to find out a little bit more about the states in the detonation. We want to find out what is the velocity of a detonation. Is it that a detonation will have a unique velocity like a flame, laminar flame, or the burning velocity was unique? You said it is something like 0.2 meters per second or 1 meter per second. What is the velocity of a detonation? Can I find out from this particular curve over here? To do that, I go to the next slide over here. Well, I tell myself, well, if I go back to the previous slide, I can draw a tangent from the initial point which is tangential to the reaction Hugoniot at the point u. When I say tangent to the point, well, this velocity is a minimum, because if I have other velocities, the velocity is higher because the slope is higher. Therefore, you say, well, u has the minimum velocity, and let us examine this point u before I can say anything about which are the states in this particular curve between A, u and beyond for which I can have detonations. Therefore, let us examine the point u first. And when I examine the point u, what is it I get? I get that the slope of the Rayleigh line is tangential to the reaction Hugoniot. Therefore, let us go back and find out what is the slope of the reaction Hugoniot and equate it to the Rayleigh line to get the point u. And if I do that, I am interested in the slope of the reaction Hugoniot. Well, the reaction Hugoniot had the equation gamma by gamma minus 1 into p by rho minus p0 by rho 0 minus half of p minus p0 into 1 over rho plus 1 over rho 0 minus q, and therefore it was equal to 0. Therefore, I differentiate this, or I differentiated d by d of 1 over rho to get the slope, because my x axis, if you saw earlier, was given by 1 over rho. Rho 0 is the reference value. Therefore, if I differentiate it, what do I get? I get gamma by gamma minus 1. I have p by rho. Therefore, if I differentiate first with respect to 1 over rho, I get p, and then I get 1 over rho into dp divided by dp by d 1 over rho, and this takes care. p0 rho 0 are the initial states which are constant. Therefore, it becomes 0 here. D by d 1 over rho of these two terms are 0, minus I get d 1 over rho of p minus p0 I take out. I differentiate. I differentiate with respect to 1 over rho, I get 1. Therefore, it is minus half of p minus p0, minus I take this to be the term and differentiate with respect to p. I get dp by d1 over rho is equal to 0. Therefore, when I differentiate this equation, I am able to get terms of dp by d1 over rho, and I would like to determine dp by d1 over rho from this equation. And when I do that, what is it I get? Dp by d1 over rho, let us go back to the previous one. I get, well, I have gamma by gamma minus 1 p. I also have half into p minus p0, which is independent of this factor, and therefore I have these two which come on the right hand side. I have dp by d1 over rho into 1 over rho, and I have this particular term minus half over here. When I add these two things together, I get dp by d1 over rho is equal to p minus p0 minus 2 gamma minus 1 into p divided by the term which multiplied dp by d1 over rho, which gave me 2 gamma minus 1 into 1 over rho minus 1 over rho 0 plus 1 over rho. This is the slope of the Rayleigh line which was tangent to the point u. That means the slope of the line 0 u is given by the particular expression which we have derived. Now, equating this slope to the slope of the Rayleigh line, mind you, this is the slope of the Rayleigh line, this is also the slope of the Rayleigh line, and slope of the Rayleigh line is p minus p0 divided by 1 over rho 0 minus 1 over rho. Why is that? If you go back and see, well, the slope of this is this equation, p minus p0 divided by this particular value, which is equal to this minus this, which is the value, and therefore I equate the two expressions together. I equate this equal to p minus p0 divided by 1 over rho 0 minus 1 over rho, and this should be able to define the properties at the point P. Therefore, I simplify it further, and how do I simplify it? Well, I have in this particular equation, if I say I have p minus p0 minus 2 gamma minus 1 p, this is multiplied by 1 over rho 0, and I have p minus p0 multiplied by the denominator over here 2 gamma minus 1 over rho minus 1 over rho 0 plus 1 over rho, and then equating the two together, well, I get this particular equation over here. It is just multiplication of the left hand side numerator with denominator on the right hand side and the numerator on the right hand side multiplied by the denominator. I simplify this. When I look at this particular expression, what is it I get? Gamma by gamma minus 1 is equal to gamma minus 1 divided by gamma minus 1, that means 1 over gamma minus 1, and therefore if I have 1 over gamma minus 1 here and here 1 over gamma minus 1, it cancels off, and therefore what is it I get? I get P minus P0 divided by 1 over rho minus rho 0. There is one particular gamma left over here, gamma P into rho from this left hand side. Therefore, what is it I get? I get the value of P minus P0 divided by 1 over rho minus 1 over rho 0 is equal to minus gamma P rho, which is the solution of the value of pressure and density at the point U. Now, if I look at this particular expression, it tells me, but I also know that P minus P0 divided by 1 over rho minus 1 over rho 0 was my Rayleigh line, which was equal to rho 0 into V0 square, and also I know that from continuity that rho 0 V0, because this is my plane of reference, rho 0 V0 is equal to rho into V1, and therefore I can write this rho 0 V0 square, rho 0 square into V0 square as equal to rho square into V1 square, or rather V1 square is equal to 1 over rho 1 square into P minus P0 divided by 1 over rho 0 minus 1 over rho, and therefore this P minus P0 is given by minus gamma P into rho. I substitute the value of minus gamma P rho over here, and what is it I get? I get it is equal to, now I have here 1 over rho 0 minus 1 over rho, here I have 1 over rho minus 1 over rho 0, therefore minus and minus I substitute plus gamma P rho divided by rho 0 square, and therefore V1 squared comes out to be gamma P by rho. Therefore, I get the value of velocity in the frame of reference of the detonation behind the detonation, namely V1, is equal to gamma P by rho. What is the implication of this? Let's debate this. Therefore, let me go to the board and see what is the final expression what I get and how do I interpret this particular point. Therefore, let's come back over here. What is it we have? We said I have the pressure over here, I have 1 over density over here, I had the initial point which is 1, 1, which we called as O over here, we had the shock Hugoniot over here, we had the reaction Hugoniot over here, we drew a tangent from here, from the initial point which was tangent over here, maybe this was your reaction Hugoniot. Let me put a color chalk on the reaction Hugoniot, that means the reaction Hugoniot is shown by the yellow line. I want to determine this particular point U. What is it I get? I get the value of P at U, that is along this. I get the value of rho at this, rho over here, and the relation I find is the velocity V1 square. That means I come back to the point, namely I get in the frame of reference of the detonation, well, the particles are moving behind it with a velocity V1. Ahead of it, the unburned gases at P0, rho 0 are moving with a velocity. Here it is P and rho over here. I get V1 square is equal to, if I take a expression, I get as equal to gamma P by rho is equal to V1 square. And what does this represent? What does gamma P by rho represent? It denotes, we would have seen earlier that when we wrote the expression for the sound speed, we said sound speed is equal to gamma P by rho in any medium. A0 squared is equal to gamma P0 by rho 0. The sound velocity behind the medium is equal to gamma P by rho. That means the sound speed in the medium processed by the detonation is A, which is equal to this. That means V1 square is equal to, that means the velocity of the gases in the frame of reference of the detonation itself, V1 square is equal to A1 square, or rather the Mach number behind of the particles processed by the detonation is unity. What is the implication of this? Let's again take a look at this particular expression, namely let us plot it over here. You have a detonation over here in the frame of reference of the detonation, that means the observer is on the detonation. Well, the velocity coming towards him is v0 from the condition p0 and rho 0. The velocity with which the gases are leaving the detonation is v1. Well, the sound speed here is equal to a1, which is equal to v1, let us say, or a is equal to v1 over here. We called it as a1, we will keep a1 is equal to v1. What is the implication of v1 being equal to a1? You know behind the detonation, we expect to have a compression of the gases, that means high pressure over here. Once the detonation moves, there will be some sort of expansion, that means in the gases here there will be expansion, and because of expansion the disturbances will try to catch up with the detonation. That means in the reference in which maybe a detonation wave is travelling, we have high compressed gases over here, therefore there is expansion of gases, therefore the disturbances here will try to meet the detonation, but since the velocity of the particles here is moving with a velocity v1, which is same as this, the disturbances can only travel at the sound speed, and since the gases are moving away at v1, well, these disturbances can never really catch up, and therefore a detonation at the point u will always travel at constant speed. Why it will travel at constant speed? The disturbances behind the detonation can never really catch up over here, because the velocity behind the detonation is same as the sound speed, and therefore disturbances cannot catch up, and therefore it will just go undisturbed or undecayed into the medium, as it were. Therefore, and the speed corresponding to u is spoken of as Chapman-Jouguet velocity. It is the constant velocity with which a detonation travels, and it is the point of tangency between the reaction Hugoniot shown by the yellow line and the Rayleigh line, which are tangent at the point u. Therefore, we tell, well, for a detonation I would like to calculate the Chapman-Jouguet velocity, and therefore I would like to calculate the velocity for a detonation, which I presume will travel at constant speed here, because the sound speed behind cannot really catch up and retard the motion of the disturbance. That is, no disturbance can catch up with the detonation front. But then we also said, well, the detonation, if I draw a vertical line from the initial point, that means I draw a vertical line over here, this is the point, I find, well, detonation can be anywhere between, let us say we said this is point A, this is point U, the detonation can be anywhere between this and this, or also anywhere between this. Why do I have to have the detonation only for the tangent? I could have a series of lines, maybe I could draw a series of lines here, maybe I could draw a line like this, this could be one detonation velocity, this could be another detonation velocity. Are all these detonation velocities possible? Therefore, we will try to find out what are the regimes in this particular compression solution for which detonations are possible. Let us do that, and that I show in the next slide over here. If you look at this particular figure, I take the point from A, and this is the reaction Hugoniot. U is the Chapman-Jouguet point, which we say for which the conditions behind the detonation, the velocity is such that the velocity is same as sonic speed at the locally under those conditions. And therefore, when I talk of this, is it possible if I say I divide it into two regions, this particular reaction Hugoniot, I divide it into region 1 and region 2. In region 1, I consider those regions which are above U. In this particular region 1, the pressure is higher than at the point U, and therefore, since the pressure is higher, the velocity behind the detonation in those regions is going to be lower, V1 is going to be lower, and since it is going to be lower than therefore the sound speed, well, the sound speed can catch up with the front, and therefore what you get is you get a strong detonation in which the pressure is higher, but the sound speed behind will cause the disturbances to catch up with the front, and the detonation will keep on decaying. Therefore, we say, well, in I you have something like a detonation which has higher pressure or sort of overdriven, but then the detonation velocity cannot be constant because disturbances behind the overdriven detonation catch up with it and cause it to decay, and therefore you have a decaying detonation which has pressure higher than the Chapman-Jouguet velocity, which Chapman-Jouguet pressure or Chapman-Jouguet velocity, and since it is a higher pressure, we call it as a overdriven detonation, but this cannot be a steady detonation propagating at constant velocity. When we look at the point between u and a, well, what is happening? You have the velocity which is higher than at u, 0.1, but then we find that the pressure is lower. Since pressure is lower, the velocity behind the detonation is going to be higher than the velocity behind the point u, that is the Chapman-Jouguet condition, and since the velocity behind the detonation is higher, it is going to be higher than the sound speed. This is not possible in practice, because in a constant area duct, there is no way I can accelerate particle velocity from subsonic to supersonic. It is just not possible, and therefore we say, well, the region 2, which corresponds to the region between a and u, cannot exist in practice. Therefore, for a detonation, only the overdriven region, wherein I cannot get a constant velocity detonation, but I get a high velocity detonation, velocity being higher than Cj, it continually keeps decaying until it reaches the Cj value. This is the detonation branch. Since we are talking of this, we can as well talk of the expansion solutions also, and we look at the expansion solution. Well, from the initial point I draw a tangent. The tangency is at point L, similar to the tangency at point u in the detonation region, and over here again the sound speed in the particulates behind the flame or behind the discontinuity is sonic. And what happens in the region 3, I can divide the expansion region B, L and so on over here, and in the region between B and L, what is going to happen? Well, the pressure is higher, the velocity behind the discontinuity is going to be lower, and therefore this is the case of a flame which is continually getting decelerated because of the disturbances catching. In the region L and beyond, well, the velocity comes out to be greater than sound speed, which cannot be met with in practice, therefore this cannot exist. Well, this is the region of the decaying flame. Therefore, putting these things together, we tell ourselves on the Hugoniot, well, this part is not possible for reasons that the velocity behind the detonation is greater than sound speed. This region is not possible because the velocity exists, velocity is again higher than the sound speed. Therefore, these two regions are not possible. Only the overdriven and Cj is possible for a detonation. So also for a flame or a weak deflagration, only the region between this point to the point L, which is the Cj point, is possible. Point u and above corresponds to overdriven detonation, u corresponds to the Chapman-Jouguet detonation. Similarly here, the point L, which is tangent is the Chapman-Jouguet deflagration, and well, you have lower velocities over here which corresponds to the weak deflagration. Well, this is about the possible states on the reaction Hugoniot, but what did we set out to do? We wanted to calculate the velocity, and we find that the velocity of a detonation, if overdriven, is going to be higher, but if it is higher, it keeps on decaying and reaches the Chapman-Jouguet value. Therefore, let us go back and calculate the velocity at the Chapman-Jouguet point. That means we would like to calculate the Chapman-Jouguet velocity of a detonation. Let me put our problem again on the board. What we want to do is, we want to calculate the velocity, the steady state velocity of a detonation, and this we find is only possible at the point u on the reaction Hugoniot, for which we just said that the slope of the Rayleigh line and the slope of the reaction Hugoniot are the same, and for which we found out that V1 behind the detonation is equal to the value of the sound speed. Now, for this the disturbances are unable to catch up together, the detonation travels at the value VCJ, which is possible. When the pressure is higher, you have a overdriven detonation, but the overdriven detonation has a velocity greater than VCJ, and in the region when we looked at the particular Hugoniot over here, we are talking of points which are greater than A, and in this region the velocities are higher, the pressures are higher, we say it is overdriven, and since it is overdriven, the velocity of a detonation is greater than the VCJ, but it asymptotically decays till it reaches the Cj value. Therefore, an overdriven detonation is not steady. We would like to calculate the steady state Chapman-Jouguet velocity for a detonation. Therefore, how do we calculate it? Let's just proceed. We have all the equations with us to calculate. Let us again go back to the Hugoniot, reaction Hugoniot. And what is the reaction Hugoniot? Well, you have gamma by gamma minus 1 into P by rho minus P0 by rho 0 minus half into P by P0 into 1 over rho 0 is equal to the heat release. The left hand side corresponds to the shock Hugoniot, the right hand side you have Q, therefore it becomes a reaction Hugoniot. Again, I am just interested in getting the value of dP d1 over rho, we have just done it. And what did we tell? Well, if we look at it, we have already calculated the value. We said P minus P0 divided by 1 minus rho divided by 1 minus rho 0 is equal to minus gamma P rho. We had 1 over rho 0 minus 1 over rho giving gamma P rho. Therefore, I inverted because I am looking at the change d rho over here is equal to minus gamma P rho, and we want to substitute the value of dP by d1 over rho when we differentiate this particular reaction Hugoniot, and when we differentiate it, what is it we get? Gamma by gamma minus 1 over rho, therefore 1 over rho when differentiated by d1 over rho becomes 1, therefore I have P plus 1 over rho into dP by d1 over rho. Similarly, on the right hand side I take it on the right hand side, Q its constant heat release, well it becomes dQ by d 1 over rho becomes 0, and I have 1 over rho 0 plus 1 over rho over here, the value of half is still lingering on, dP by d1 over rho plus I have d by d1 over rho is 1 by this P by 2. This becomes the equation from which I get the value of dP by d1 over rho. This is same as what we did earlier. Now I substitute the value of dP by d1 over rho is equal to P minus P0 into 1 minus divided by 1 over rho minus 1 over rho 0, and this is equal to minus gamma P rho. I substitute the value of this as minus gamma P rho, the value of this as minus gamma P rho, and what is it I get? Let us substitute. Well, here I had the expression for dP by d1 over rho, I had the expression for dP by d1 over rho, I am substituting as minus gamma P rho, and when I substitute it, I get 1 over rho into minus gamma P rho, rho and rho gets cancelled, that is P plus minus gamma P over here, and similarly I have dP by d1 over rho, I substitute over here, I substitute over here. Let's take a look at the left hand side. Well, rho and rho get cancelled, I get P over here, I get 1 minus gamma is equal to half into 1 over rho 0 plus 1 over rho into this value plus P by 2, and therefore if I further simplify this expression, I get, now I expand it out, I put gamma P rho into 1 over rho and I have 1 over rho 0, I find yes, if I take a look at 1 over rho 0 over here, that is P by rho divided by rho 0, I have P over here, I have P by 2 over here, therefore I get 1 over 2, let's just expand it out, I get minus gamma P into gamma minus 1 comes over here into P by 2, or rather you find that 1 minus gamma, you have gamma minus 1, you have minus 1, therefore minus gamma P on the left hand side, minus half gamma P, because I take the value of rho over here minus gamma P over here, minus 1 over rho 0 into minus gamma P rho divided by rho 0 over here plus P by 2, and further if I look at this, I bring this on this side, I get gamma P on this side because this becomes plus, and I take this on the right hand side, half of gamma P rho by rho 0, this gives me gamma P by 2 plus p by 2, that is p by 2 into gamma plus 1, and this becomes my equation. And when I take a look at this particular equation, I find I have p on the left hand side, I have p on the right hand side, I have 2 over here, I have 2 over here. Therefore, I can cancel p and p, I can cancel 2 and 2, and what is it I get? I get gamma rho by rho 0 is equal to gamma plus 1, or rather rho by rho 0 is equal to gamma plus 1 divided by gamma. Rather, what is it I get? I get rho by rho 0 is equal to gamma plus 1 divided by gamma, or rather I am able to get the density behind the detonation. That means for the CJ condition, I get the density behind my detonation to density upstream is equal to gamma plus 1 divided by gamma. Now, in this case, I also presume that the shock is sufficiently strong. We had we did not consider the effect of weak shocks, because the weak shocks cannot promote chemical reactions and form and give heat release. But if you are considering a strong shock in which chemical reactions are not occurring, we had the expression rho by rho 0 is equal to gamma plus 1 divided by gamma minus 1, and therefore what is it we see? Let's examine this expression before we proceed any further. We are finding that whenever you have a detonation which is propagating at the Chapman-Jouguet velocity, the initial condition is rho 0, the condition behind the shock is rho, behind the detonation in which let us say chemical reactions are also occurring is rho. We get the value of rho by rho 0 is equal to gamma plus 1 divided by gamma. Earlier we have seen the case, if I have a shock wave, let us say I have a shock wave which is propagating in an inert medium of properties like the physical properties are similar to the gas mixture in which it is propagating, but there is no reaction happening. That means it is propagating with a velocity v in a medium of rho 0 p 0, and what is the condition behind the shock wave over here? It is without reaction. We find that rho by rho 0 is equal to gamma plus 1 divided by gamma minus 1 plus 2 over the Mach number of the front square. We said it is sufficiently strong because it is promoting chemical reactions. We say Vcj is equal to V. We found out that maybe for a shock wave the density is gamma plus 1 divided by gamma minus 1, whereas when we are talking of a detonation, the density ratio is gamma plus 1 divided by gamma minus 1. Therefore, when I say rho by rho 0 for a Chapman-Jouguet detonation divided by rho 0 for a shock wave traveling with the same speed as the Cj, that means for a shock wave traveling with at the same Cj value, you find that the value is equal to, you find, well, it is equal to gamma plus 1 divided by gamma plus 1 divided by gamma minus 1, or rather, because this is negligible, because Mach numbers are quite high, it gives me gamma minus 1 divided by gamma, or rather we find that the density behind the detonation is much smaller. That means if I take gamma as 1.4, it gives me 0.4 divided by 1.4, which is of the order of 0.3. That means the density behind a Chapman-Jouguet detonation is something like 1/3 the value of the density of a shock moving at the same speed in a similar medium. Therefore, the density decreases from behind the shock to the zone of chemical reactions. Now, in a similar way, I can also calculate the pressure, I can also calculate the other parameters. Let's just calculate the pressure and then let's calculate the value of the Cj velocity. From the Rayleigh line, we also find that rho 0 v0 squared, that is the Chapman-Jouguet velocity square, is equal to p minus p0 into 1 over rho 0 minus 1 over rho. This is the Rayleigh line. Therefore, I have Vcj square is equal to, now I take p0 outside, I take rho 0 outside, and I get p0 by rho 0. This rho 0 cancels with this rho 0. I get p0 by rho 0 divided into p by p0 minus 1 into 1 minus rho 0 by rho, which is equal to the value which I have written over here. The thing what I have written is, I take the value of rho by rho 0 behind the detonation we just now calculated as equal to gamma plus 1 divided by gamma, and therefore I substitute for rho by rho 0 over here. And therefore, now when I look at this equation, I get P by P0, I get P0 by rho 0 as the initial condition, I get the velocity of a detonation, that is the Chapman-Jouguet velocity. Therefore, I solve this particular equation, and what do I get? I move the value of rho 0 on top over here, P0 in the denominator over here. I get VCJ squared into rho 0 by P0 is equal to, I get the value of gamma plus 1 minus gamma divided by gamma plus 1. It gives me 1 over gamma plus 1. Therefore, gamma plus 1 into P by P0 minus 1 over here, which means I should be able to get the value of P by P0 from here. I can solve this equation, and what is the value I get? I get P by P0 minus 1 is equal to gamma by gamma minus 1 into the VCJ squared by A square. How did that come? We have P0 by rho 0. If I put gamma P0 by rho 0, it is equal to A0 square. That means I multiply numerator and denominator by gamma, and therefore I get gamma VCJ square by A0 square by VCJ square divided by A0 square is equal to the Mach number of the detonation, that is mCj square. Therefore, I get gamma mCj square, and therefore, what is it I get? mCj square is equal to P by P0 minus 1 divided by gamma minus 1 from the previous expression, or rather P by P0 is equal to gamma by gamma plus 1 into mCj square minus 1. This gives me my pressure ratio. If I were to look at the pressure ratio as the Mach number of my Cj detonation, that is the Mach number of the detonation keeps increasing, my pressure ratio also goes up. But if you compare a strong shock traveling at the same velocity, at the same Mach number as the detonation, you know that we have derived this expression earlier, P by P0 is equal to 2 gamma plus 1 into m square minus 1 for an unreactive shock. Therefore, looking at an unreactive shock traveling at the same Mach number as the Mach number of a Chapman-Jouguet detonation, we find, well, P by P0 is 2 gamma plus 1. In this case, it is gamma by gamma plus 1. That means, and you know m is a large number, therefore we find that the pressure behind a detonation is half the pressure behind a shock traveling at the same speed. Therefore, there are two conclusions that we draw from this, namely, one is the pressure behind a detonation is less than the pressure behind the shock traveling at the same velocity. Second, we also found that the density behind a detonation is something like 1/3 the density behind a shock traveling at the same Mach number as the detonation itself. Having said these two, you know, our aim was to be able to calculate the Chapman-Jouguet velocity, or rather the Mach number of the detonation. Therefore, but before we do that, let us take a look at temperature. We know we have just now derived the value of P by P0 is equal to gamma by gamma plus 1 into the Mach number square minus 1. 1 is a small number, I can neglect it compared to the high velocities, high Mach numbers over here. We said rho by rho 0 is equal to gamma plus 1 divided by gamma. Therefore, T by T0 I can express by using the gas equation, P is equal to rho RT, as T by T0 is equal to P by P0 into rho 0 by rho. This gives me the velocity as gamma squared by gamma plus 1 square into mCj square. And if I look the same thing for a shock, that means an unreactive shock at the same Mach number, I get P by P0 is equal to 2 gamma by gamma plus 1 into m square. Rho by rho 0 for an unreactive shock is equal to gamma plus 1 divided by gamma minus 1, because here rho by rho 0, and the value of the temperature rise in a detonation, T by T0, T0 is ambient temperature behind a detonation, divided by the temperature rise behind an equivalent shock wave traveling in an unreactive medium of similar properties but without heat release, is equal to gamma by 2 gamma minus 1, which is almost twice. In other words, the temperature behind a detonation is much higher than an equivalent shock traveling at the same speed, but the pressure is much lower at around half and the density is around 1/3. Having done these two things, that means we have determined the density and the pressure behind a detonation. We still want to determine the velocity of the Chapman-Jouguet detonation, and let us do that now. we find that VCJ square, that means again we are looking at the Rayleigh equation, VCJ square is equal to 1 over rho 0 square into P minus P 0 into 1 over rho 0 minus 1 over rho, and this we could also write as equal to P minus P 0 into 1 over rho 0 minus 1 over rho is equal to something like minus dP by d 1 over rho, because it should have been 1 over rho minus 1 over is equal to dP by this, and therefore I can say VCJ square is equal to minus 1 over rho 0 square into dP by d 1 over rho, because here there should have been a negative sign because I am considering the density d rho is equal to d 1 over rho is equal to 1 over rho minus 1 over rho 0. Therefore, I have dP by d 1 over rho is equal to gamma p rho. We have used this earlier, and therefore I can write VCJ square is equal to 1 over rho 0 square into minus gamma p rho, which is equal to something like minus gamma p rho divided by rho square. That means I have an expression for VCJ square in terms of p and rho. We have determined these quantities, and therefore let us substitute them again and try to find out. That means we have VCJ square is equal to gamma p rho by rho 0 square. We also had the expression of p by rho when the Chapman-Jouguet velocity is high, it is anyway supersonic, mcj is a high number, is equal to gamma by gamma plus 1 square into VCJ square. You substitute it in the reaction Hugoniot, and what was the reaction Hugoniot? Gamma by gamma minus 1 into p by rho minus p0 by rho 0 minus half into p minus p0 into 1 over rho 0 plus 1 over rho is equal to q. Let us consider this expression because the pressures behind a detonation are rather high, as we saw on the reactive Hugoniot which was sketched on the board a few minutes ago, and therefore since P is very much greater than P0, I can neglect P0 over here, I can neglect P0 over here, and therefore the equation becomes gamma P by gamma minus 1 rho on the left hand side, and taking this on the right hand side I have half P into 1 over rho 0 plus 1 over rho plus Q, same equation for when P is very much greater than P0. And now what I do is I just have this equation in which this term is not there, this term is not there. I substitute the value of P by rho, which I found is equal to gamma by gamma plus 1 square into VCJ square. This becomes my left hand side, and now on the right hand side I have half P into 1 over rho 0 plus 1 over rho plus Q, and this I have P by rho 0 plus P by rho on the right hand side. Well, I already have the expression for the value of rho by rho 0 is equal to gamma plus 1 by gamma, and we just now saw that gamma p by rho is equal to rho 0 square is equal to VCJ square, and therefore if I were to substitute rho by rho 0 here in terms of gamma plus 1, I get the value of p by rho 0 is equal to 1 over gamma plus 1 into VCJ square, and I already know the value of p by rho from the previous expression. On the last slide we got it as equal to gamma by gamma plus 1 square into VCJ square. I substitute the value of p by p0 as equal to 1 over gamma plus 1 into VCJ square. I substitute the value of p by rho as equal to gamma divided by gamma plus 1 square into VCJ square over here, and what is it I get? The final expression. When I substitute this, we have seen the left hand side. I substitute 1 over gamma plus 1 plus gamma by gamma plus 1 square into VCJ square is equal to Q. This becomes my Hugoniot, or rather Q becomes equal to gamma by gamma minus 1 into gamma divided by gamma plus 1 square into VCJ square minus half into 1 over gamma plus 1 plus this particular term into VCJ square. I take VCJ square common over here. I take all the factors of gamma over here, gamma by gamma minus 1, gamma by gamma plus 1 square minus half into 1 over gamma plus 1 minus you again have minus half into gamma plus 1 square. Now I take gamma minus 1 gamma plus 1 square outside, I get gamma square over here minus you have gamma plus 1, therefore I multiply the numerator by gamma minus 1 into gamma plus 1, and here I have gamma plus 1 square, therefore I have numerator gamma, I multiply numerator by gamma minus 1. I simplify this expression. If I simplify, this becomes gamma square minus 1, this becomes gamma square minus gamma. The net result I have gamma plus 1 by 2 for this term within the square bracket, and therefore Q becomes equal to 1 over gamma plus 1 into gamma plus 1 square into gamma plus 1 divided by 2 into VCJ square. Gamma plus 1 cancels with this particular gamma. I get gamma minus 1 into gamma plus 1, that is gamma square minus 1 into VCJ square, and of course I have 2 over here, and therefore the expression I get is Q is equal to VCJ square divided by 2 into gamma square minus 1, or rather the Chapman-Jouguet velocity square is equal to 2 into gamma square minus 1 into Q. That means I am able to get the expression for VCJ square. And what does it give? Let me write the expression on the board. I get, through the manipulations of my reaction Hugoniot, at the point U, I get at the point U the value of VCJ square is equal to 2 into gamma square minus 1 into Q, or rather VCJ is equal to under root of this. Therefore, once I know that the heat release from combustion, I also take the value of gamma, which for the present I have assumed to be the same ahead of the detonation and behind the detonation. I can calculate the unique velocity with which a detonation propagates at steady conditions, which is the VCJ value. And so we are able to get the value of VCJ, we are able to get the value of rho Cj by rho 0, which we saw was equal to gamma plus 1 divided by gamma. We are also able to get the value of Pcj, that is the velocity behind the Chapman-Jouguet detonation, divided by P0, also in terms of the values over here, which I just now wrote. Therefore, we are able to get the properties of a detonation corresponding to the Chapman-Jouguet point. If the detonation is overdriven, well, the pressure is higher. If the pressure is higher, well, the density is higher, but it cannot propagate as a steady state detonation. It continually decays in strength till it asymptotically reaches the Cj value. Therefore, in this class we have been able to calculate the properties of a Chapman-Jouguet detonation which propagates at steady values. In the next class we will take 1 or 2 examples on how to calculate these values, and also we will see what could be the structure of a detonation when we are considering the one dimensional wave which is propagating, because we have done something. We find that the density behind the detonation is less than of a shock, the pressure is less, only thing is that the temperature is higher. We would like to plot and see how these things vary in a detonation. Well, thank you.